So these are Chapter 21 solutions. I'll upload both a PDF and then the screencast on my website. This is for AP Physics 2. So we went over the conceptual questions quite in detail in class. I thought you did a really nice job of that. That's what these are here. And now to the problems. And again, we went over most of these in class. So you may have solved them a little bit differently. There's a lot of mathematical formulas where you could have done that. So for number 13, you had a proton. It was moving at a certain speed. It was brought to rest by an electric field. So that should tell us that it's losing kinetic energy and gaining potential energy. So the change in kinetic would equal the change in potential. So those are the relevant formulas. And that's how I get 3,340 volts is the potential difference that the charge has to travel through. So for this part now, if I look at this, this comes out to this many joules, but to convert to electron volts, I just divide by that number of joules as in 1 electron volt. So basically the idea is if an electron or proton travels through this potential difference, it would have that amount of energy. That's a very small amount of joules, as you can see, but a reasonable number for an electron volt. So it's just something that which is useful sometimes when you don't want to talk about everything to the -18th, -19th power. For problem 16, I did this on the board. So again, I think Danny Heitmeyer did this a little bit different way. First, I got the electric field. Then I used this formula for capacitance. There was no dielectric, so I didn't need a K here. So that got me the capacitance. And then I used this formula for capacitance to find the amount of charge on each plate. You could combine these to solve using the electric field strength to solve for the charge as well. I think that's what Danny Heitmeyer did. Problem 21 was to find the potential at this point. So this charge is 4 centimeters away. This charge is 3 centimeters away. This charge, thanks to the miracle Pythagorean theorem, is 5 centimeters away. They all are plus 2 nanocoulombs. So essentially I do a summation of all these kq over r's. So this k is 9 times 10 to the 9th. Each charge is 2 times 10 to the -9th. And the distances are 0.04 meters, 0.03 meters, and 0.05 meters. So I get those voltages and end up adding them up to 1,410 volts. For 31, I looked at the picture, realized I have a 200 volt potential difference over 0.02 meters, and that's 10,000 volts per meter. For number 45, we had a capacitor in a circuit. It was 10 microfarads. It was then asking to find the total charge that flows. So in this particular case, what I'm looking at is, at least initially, we'd have something completely uncharged. So 0 coulombs. If we know this capacitance and this voltage, that'll let us know how many charges it ends up with, which is 1.5 times 10 to the -5 coulombs. So that's the total amount of charge that would flow by the time this becomes fully charged. For number 46, we've got a 1.2 nanofarad capacitor that increases by 3 nanofarads. You can see I initially wrote increases to 3 nanofarads, which is why I had to change my answer. So it increases by 3. That means it's a final capacitance of 4.2. So I think this is what the group was trying to do on the board, and recognize that capacitance is equal to this K E sub 0 A over D. Well, the E sub 0 A over D is all going to cancel out. So I basically get K1 is proportional to capacitance 1, K2 is proportional to capacitance, or K1 is proportional to capacitance 1, K2 proportional to capacitance 2. K1 was air, so it's 1.054, and then this was not air. You got a K2 of 3.5. Problem 51, after a 12 volt battery is removed, the potential difference is still 12 volts. We went over this in class. Unfortunately, this cut off the side of my paper here, which is a pain in the butt. But the book answer was wrong. If the Teflon's dielectric constant is 2.0, then because the charge cannot change if the battery is not connected, but with a dielectric the capacitance would go up, then the voltage would actually have to decrease. So the new voltage would be 6.0 volts. 63, this is to get the potential energy at that point, it's Q times V, but I need to get the V first. So that's a summation of the KQ over Rs. The K is here, the Q is here, the R is here, which I got using Pythagorean theorem of 2 nanometers on this side and 0.5 nanometers on that side. That gave me about 0.6999 volts, but there are two charges. So each charge adds 0.6999 volts, so that's a total of 1.4. Multiply that by the charge of the electron, and I have a negative potential energy. 73 we went over in class. I squished this too much, but basically if I think of energy, the potential energy here is going to be increasing by a certain amount. How much? Well, the potential energy is going to be increasing because we go, the potential energy is going to be decreasing by a certain amount because we have a positive charge going from a high potential to a low potential. So I use this as my general energy formula. Ke plus potential energy at the beginning equals Ke plus potential energy at the end. I know the kinetic energy at the beginning. I got this from saying Q times 30 here equals Q times negative 10 here. Because this is the term I want to isolate on the right side, I move this over to the left side. So basically that ends up being this Q times 40. So essentially that's how much potential energy I'm adding to the initial kinetic energy to get the final kinetic energy. And that is equal to 1/2 mv squared, and that's 101,000 meters per second. So again, I could pick this at 0 volts, and this is plus 40 volts higher than that. That's another way to think about it. 75 is the one we didn't get to go over. So it talked about the capacitor voltage being 5,000 volts, the velocity of the proton being 300,000 meters per second going to the right. So if this is due in the middle, right in the middle, it's asking you to find the impact speed of this. So we know that EI is equal to EF, that's energy. So at the beginning we have kinetic energy because it's moving, and potential energy because it has some potential to accelerate toward that negative plate. In the end, it's all going to be kinetic energy because it will be right on top of that, or actually below that negative plate. So since the proton moves through 2,500 volts of potential difference to get to the negative plate, I can find the change in potential energy. That's a positive charge. The change in voltage is negative 2,500 volts because I'm going to the negative plate. So that means the potential energy decreases by that amount. So therefore the change in kinetic energy would be an increase of that amount. So then the final kinetic energy is equal to the initial amount plus the change. And that's my total final kinetic, energy. That's the initial part with 1/2 mv squared, and that's the change. And that gets me my final kinetic energy. Divide by the mass, like so. Get around 7.5 times 10 to the 5th meters per second. So it definitely went a lot faster. You could have figured this out also by taking a look at the horizontal speed and then recognizing how much force would be acting on that proton and the distance it would be accelerating, and find the final vertical speed. And then you could use Pythagorean theorem for that. So you could have done that if, again, I think that would be a more difficult thing to do because we don't know this distance. Sometimes they might give you that. So in this case, I think keeping it purely an energy problem is what would work best. So hopefully this helps you out. There's a lot of stuff going on.